Hi, thanks for tuning in. Today I'll be talking about joint work with Mark Bunn and Marco Carmosino on efficient, noise-tolerant, and private learning via boosting. Our goal in this work is to construct private pack learners following the framework of KLNRS. So we want an algorithm to solve the following problem. There's some unknown binary classifier f, and we'll want to find a hypothesis h that has good agreement with f with respect to some unknown distribution d over f's domain. We also want our learning algorithm to be private in that it should protect the privacy of individuals in the training data. So consider two parallel runs of our algorithm on neighboring samples S and S prime, where the only difference between S and S prime is that we've swapped out a single example. So here, the second example contains Marco's data, and this is our sample S, and then in neighboring sample S prime, we've swapped out Marco's data for Mark's data instead. And we want it to be the case that the distributions over hypotheses output by our algorithm on these neighboring samples will be close. More specifically, we'll say that our learning algorithm is epsilon delta differentially private if for all neighboring data sets, the probability of seeing a particular hypothesis in one run is no more than e to the epsilon times the probability of seeing it in the parallel run, allowing some probability delta of privacy failure. We're going to construct these private pack learners via boosting, just a technique for constructing strong pack learners from weak learners. So what's a weak learner? A weak learner takes a sample S along with a distribution D over S and outputs a hypothesis that agrees with F with probability gamma greater than a coin flip with respect to that same distribution D. Boosting consists of successive adaptive calls to this weak learner on varying distributions. It looks something like the following cartoon. So we start with some distribution D0, which is typically the uniform distribution over the sample, and call our weak learner on this sample and this distribution. Weak learner outputs some hypothesis H1. We then add H1 to our collection of hypotheses H and run a reweighting algorithm that uses this collection of hypotheses to reweight the distribution over examples, emphasizing those our hypotheses have performed poorly on so far. This reweighting algorithm outputs a new distribution D1, which we again give to the weak learner, which outputs a hypothesis H2. We add H2 to our collection, and so on and so forth for T rounds. After T rounds, we output our final hypothesis HT, which is an aggregation of the hypotheses produced at the intermediate steps of the boosting algorithm. So in this work, we give a simple framework for differentially private boosting. Prior work on private boosting by DRV required explicitly privatizing the output of both the weak learner and the reweighting scheme. This sort of affected utility of the boosting algorithm. In addition, it affected the complexity of the analysis. Notably, we release no information about the intermediate distributions, and so we only need to privatize hypotheses, at least explicitly. And this leads to a more modular framework that can capture a number of reweighting schemes. We also apply this framework to the task of privately learning large margin half spaces, and achieve sample bounds comparable to the best known for this task from NUZ. In addition, our learner can tolerate random classification noise, but we'll omit discussion of noise tolerance in this talk just due to time. Finally, we can give generalization guarantees for the hypotheses produced by our booster, just following from known connections between privacy and generalization, specifically the results of B and SSSU. So combinatorial generalization arguments can just be avoided entirely. Our framework shows how to boost a private weak learner to get a private pack learner by decomposing the boosting process into more easily analyzed components, beginning with a single round of boosting. So here, when I say a single round of boosting, I mean one that begins with a call to the reweighting algorithm, followed by a call to the weak learner, which returns a hypothesis. So that's a single round of boosting. And by known results for composition of differentially private algorithms, we can show that if one round of boosting is differentially private, then a booster running for T rounds is private for a looser privacy parameter. So this means that we only really need to show privacy for a single round of boosting. So what does this entail? We'll consider parallel runs of a round of boosting on input neighboring samples S and S prime. Again, we need it to be the case that when the weak learner is given the output of the reweighting algorithm on neighboring samples, that it produces distributions over hypotheses that are not too different. To enforce this, we define two requirements, one for the reweighting algorithm and one for the weak learner. We define a notion called slickness, where we say that a reweighting scheme is 1 over alpha n slick if, on neighboring samples, it produces distributions with statistical distance bounded by 1 over alpha n. We also require a privacy notion from the weak learner, so it has to satisfy the normal definition of a weak learner as a starting point, but it should also hold that the distributions over hypotheses output by the weak learner are similar not just when it's given neighboring samples, but when it's given input distributions over those samples that may not be the same, but are close in statistical distance. This way, if we compose an epsilon 1 over alpha n private weak learner with a 1 over alpha n slick reweighting scheme, we get that the resulting composition is epsilon differentially private. So how are we going to enforce this slickness definition for a reweighting scheme? We'll look to smooth boosting algorithms. So a reweighting algorithm is 1 over alpha n smooth if for every distribution it outputs, the distribution assigns probability less than 1 over alpha n to all examples. There are a number of these algorithms in the literature. Smooth boosting has a bunch of interesting connections to hardness amplification, noise-tolerant learning, agnostic learning, none of which we will have time to get into, unfortunately. But the important thing here is that intuitively, the fact that these algorithms assign limited probability mass to any given example means that no possibly noisy example has too much influence on the hypotheses output by the weak learner. So in other words, the hypotheses can't overfit to any particular example. Like the smooth boosting algorithm of BHK, our slick reweighting scheme makes use of Brookman projections. So let's define those real quick. The Brookman projection of a distribution D into the set of 1 over alpha n smooth distributions is the 1 over alpha n smooth distribution D prime, minimizing the KL divergence from D to D prime. This is like minimized over all 1 over alpha n smooth distributions. These projections are how smoothness is enforced both in BHK and how slickness is sort of enforced in our algorithm. So how does this work? Like, what does this reweighting algorithm actually look like? So it takes as input the sample and the set of hypotheses produced so far, and it'll start from the uniform distribution over examples. Then for each example, it'll compute a score and that's sort of meant to represent how well the hypotheses have done on that example so far. So how many of them were correct. The weight on that example will then be adjusted down based on that score, as well as some learning rate lambda. What we end up with after this is not a distribution, let alone a smooth one. So we Brookman project the resulting measure back into the space of 1 over alpha n smooth distributions. And that's the distribution we return. And we can show that this algorithm satisfies 1 over alpha n slickness. Cool. So with a reweighting scheme that satisfies our definition of slickness, we get the following theorem. If you give me an epsilon 1 over alpha n private weak learner with advantage gamma, then our boosting algorithm runs for t about log 1 over alpha over gamma squared rounds of boosting using the 1 over alpha n slick lazy Brookman projection reweighting algorithm. And this is sufficient to guarantee that our algorithm produces a hypothesis with training error less than alpha, and that the algorithm in its entirety is epsilon root t differentially private. So that was, we had got a guarantee here on the training error, but we can then use known connections between privacy and generalization, namely the results of BN SSSU, to guarantee the hypothesis will generalize to the underlying distribution with good probability. Cool, so that's our boosting framework. Now we'll talk about the application of our framework to the task of privately learning large margin half spaces. Here, the target function f we'd like to learn is a d-dimensional half space defined by a unit vector u. And we're going to assume that f has margin at least tau with respect to the distribution d over examples. We give a private weak learner for the setting and show that plugging it into our private booster gives a pack learner requiring n in softo 1 over alpha epsilon tau squared examples. And that's to learn f with an error alpha and with privacy loss epsilon. This roughly matches the sample complexity of the private half space learner of NUZ, but by way of a much simpler and noise-tolerant algorithm that can also be generalized to norms other than the L2 norm. Okay, so I claimed our weak learner was simple, so let me try to explain how it works in two pictures. For those familiar with the half-space weak learner of Servetio 01, we're just going to privatize its hypotheses by poking them with some Gaussian noise. So let's say this is our sample data, where we have positively labeled examples in our half space, negatively labeled examples outside. We negate all negatively labeled examples and take the center of mass to get this vector z. We then perturb z by Gaussian noise nu to get the vector z hat. We normalize z hat to be a unit vector, and then return the hypothesis that on input x outputs the sign of the inner product of x with this normalization of z hat. We can show this weak learner has advantage on the order of tau, so long as we take our sample size n to be large enough. Our boosting theorem then has us run for log 1 over alpha over tau squared rounds to get our error alpha, and privacy loss root t epsilon. So to achieve target privacy epsilon star, we have to take n larger than 1 over alpha epsilon star tau squared, and this suffices. Okay, so in conclusion, we gave a modular framework for differentially private boosting that improves upon prior work both in simplicity and concrete parameters. We can show generalization for boosted learners without requiring explicit analyses of VC dimension or Rademacher complexity or things like this, just using privacy. And we showed that our framework gives a simple, noise-tolerant private half-space learner without sacrificing sample complexity. Thanks so much for your attention, and I hope to see you at the conference.